All right, we had a request to do mechanism, and here's the layout you'll see on the final. Every mechanism you choose, you have a choice of two, and the wording is not exactly this, it's even more explicit. The words are, choose one of the following two mechanisms. Do not choose both. Only your first choice will be graded. It says that. And as I was telling this class earlier, if you do start one and you don't like where you're going with it, just put an X through it and do the other one. Do not do both. You will not finish the exam and you will not pass the exam. So let's not do that. So the class consensus was to try the first one here. They thought it was a little more straightforward. So we're going to choose that first one. And you can start your mechanism up there. And yes, there will be titles that roughly correspond to the titles in the textbook to help jog your memory. And I'm also going to point out, when I use sulfuric acid, I think on every test that you've had to do a mechanism with sulfuric acid, I don't draw it that way. I always show you that you got to break the bond between H and O sometime during the reaction. So that will be more like what you see on your test. And yes, you can start your mechanism in the box. That's a nice way to let me know which one you're doing too. And I've got a blank version in the notes of this, and then I redrew sulfuric acid, but that's not a big change. So remember, you got to hydrate this alkene first. And we're going to make the cation on the second carbon. And we got to get to that alcohol. You got to get the oxonium first. Please don't try to take the H off the water too early. And here's your oxonium. What takes the H off of it? Yeah, this conjugate base of sulfuric acid you made in the first step. And come around and neutralize. That's 4. I know. The majority of the points are in the next part. So the next part, you've got to, the most important thing to remember, you must make a chromate ester. Chromate ester will have, it'll look like the chromic acid that's here, except one of the H's is replaced with this carbon group when you're done. That's what esters are. There's a carbon in the place of an H, of an acid. Step 1, you can do on the original question up here. You've got to protonate the chromonyl. It's like carbonyl, but it's the chromium version. And why don't you show me that that becomes this. Oxonium. Didn't touch that one. Lone pair on the O attacks chromium. So the alcohol is now going to be bonded to chromium, as you know you need to do. And you're going to get this result here. Another oxonium. Oh, don't want red. Chromium still has the double O on top, has an OH to the right, has an OH underneath now, and one to the left. Don't forget the oxonium. And don't forget, when you made this, you also made a sulfate again, because you have to neutralize your oxonium. There's a lot of oxoniums then neutralizing in this one. This is our second time. Make oxonium, then neutralize it. And you're not at the chromate ester. You're not there yet. Now, one of your OHs, you should sew the bond to H because you need to remake the double bond to O. This is dehydration. If you watch this morning's video on hydrate formation, then you'll see this is the hydrate of a chromate ester. It needs to be dehydrated. And we've done that mechanism. You need to make it lose water. Why? Sorry. Here we are. What do I mean by losing water? Here we go. Move that down. Okay, a little severe. Here's your goal. You want it to look like chromic acid again, which means you got to strip off water. You need an acid-base pair, the same acid-base pair you've been using the whole mechanism, sulfate, sulfuric acid. Grab an H, make a pi, and normally a leaving group would leave here, but this leaving group doesn't like leaving when it's hydroxide. It needs to be water. And yes, if in your mind you say, my goodness, that looks like a tautomerization, then you make me very happy because you're finally starting to group mechanisms, which helps them become easier to learn. Yeah, acid catalyzed dehydration is like the virtual twin of tautomerization. And now you've got your chromate ester. All you have to realize now is that for that to become this, the ketone, I'll draw the ketone again down here. This H has got to go away. Clearly, there's no H on that position in the end. And yeah, there's clues about what grabs the H. You're making hydronium. I don't see hydronium yet, do you? Have we made hydronium yet? No, it's time. And you can use the water you just made. You made water right here. Here, OH picked up a proton and became water. That'll make hydronium. If this doesn't look like tautomerization, then, you know, keep studying till it does. Grab H, make pi. That's the same start as tautomerization. Then some bond breaks at the end, right? And there's your chromium with only 3 O's left. That's your other 2 products. You don't have to draw them. They're already drawn at the top of the screen, but I'll show you. Here they are. Hydronium, and there's an H with a CR and 3 O's. That's the condensed formula for what's left over here. And there's quite a bit to this mechanism, but I just want to keep telling you, it's a reaction mechanism that is common to a lot of reactions called condensation reactions. All the way up to here, where you made this molecule in water. That's condensation. And condensation reactions make every large biological molecule, proteins, and like cellulose for carbohydrates and glycogen. That's how we store glucose. They condense things together. And it's the same mechanism every time, whether it's lab chemistry or biological chemistry. So yeah, that's how things work. And there you have it. I'm thinking this might be a 12-point page because there was a little more than 10 points worth here. So I'm thinking this would be a 12-pointer. Oh, I went to the pretty wrong page. I think we're just wasting a lot of time for changing titles now, so we're going to leave it, okay?
How much is the